Hello everyone, my name is Shen Xiaoyi and I'm from Digital Signal Processing Lab of Nanyang Technological University. Today I'm going to present a hybrid approach to combine wireless and earcup microphones for ANC headphones with error suppression module. First, I will introduce some background of active noise control headphones and some practical challenges. Then I will introduce the proposed methods, and some simulations and experiment results are shown in these presentations, and at last a conclusion will be made. With the growing panic of COVID-19, more and more people choose to work from home. However, the noisy environment makes people hard to concentrate on their work and lives. The noise coming from the household appliance, traffic noise coming from outside of the windows, and the construction noise coming from the neighbors makes us exhausted. An ANC headphone is a good choice to block the annoying noise. A conventional ANC headphone is composed of a reference microphones, secondary speakers, and error microphones. The reference microphones are used to pick up the reference signals and then send it to the ANC controllers. And the secondary speakers are used to play the anti-noise generated by the ANC controllers. And the anti-noise has the same amplitude but opposite phase as the reference signals. When these two signals meet together, they cancel each other. And the error microphones are used to collect the error signals, and then it is used to update the coefficient of ANC control filters. There are some existed problems in the ANC headphones. If there are multiple noises exist in the environment, they were mixed together and then received by the one reference microphones. These reference signals always have low signal-to interference ratios, which will degrade noise reduction performance of ANC headphones. And also, the low distance between the reference microphones and the secondary speakers brings some time-constricted problems for the ANC algorithms. So here we use wireless microphones to place in front of the noise source to replace the conventional microphones on the ear cup. The picked up reference signals by the wireless microphones can have a very high signal-to-interference ratios, and the wireless receivers can place close to the ANC controllers. However, if there is an uncreated noise occurring in the environment which is not picked up by the wireless microphones, it still brings the degradation of the noise reduction performance for the ANC headphones. So here we proposed our methods to use the combination of the wireless microphones and earcup microphones implemented with an error separation modules. The block diagram of a hybrid approach to combine the wireless microphones and the earcup reference microphones are shown in the figures. The wireless microphones are placed in front of the noise sources and then send the wireless reference signals to the receivers. Each received reference signals are equipped with individual control filters, and the additional earcup reference microphones are picked up the reference signals and then equipped with another control filters. An error suppression modules are applied in this approach to provide the separated error signals to each control filters to update the coefficient of the control filters for each reference signals. Compared with the previous works, we have combined these two microphones, and then error suppression modules are used to improve the convergence performance of each control filters in ANC algorithm. The output of the control filters is calculated with the received wireless reference signals and the earcup reference signals, and the anti-noise is a summation of all the outputs of the control filters. Ym denotes the number of the potential noise sources, and the Ym is the output of M's cultural filters, and the Yr is the output of the cultural filters for the earcup reference signals. All the cultural filters are updated by the filtered X list mean square algorithms, and as shown in equation 3, and the filtered reference Xm and Xr are estimated by the secondary path, which is measured offline. The block diagram of error suppression modules are shown in figure. There are two parts of error suppression modules. One is the reference signals picked up by the wireless microphones, and one is the error signals picked up by error microphones. The output of the modules are the separated error signals, which is correlated with its related reference signals, and then they are used to update each of the cultural filters which related to these reference signals. This will improve the convergence performance of each cultural filters, compared with all the cultural filters use the same error signals to update the coefficient. The M separated error signals is generated by the filter HM as shown in the equation 5, and the least mean square algorithm is utilized to update the cultural filter of the HM. The misalignment of the cultural filters for the separated error signals is close to zero, while the cultural filters with mixed error signals is related to the variance of the residual errors components. The simulation's results shows the difference convergence performance for the separated error signals and the mixed error signals. The simulation is taken to validate the efficiency of the error suppression modules. We suppose there are three noise sources in the environment. Noise source 1 is a white Gaussian noise, and noise source 2 is a 300 to 500 Hz broadband noise, and noise source 3 are the multi-tone noise. The sampling rates are set at 16 kHz for the simulations, and the step size for the cultural filters of wireless reference signals and the cultural filter for the earcup reference signals, and the step size for the error suppression modules are set at these values, and all the primary paths and secondary paths in the simulations are all measured from a normal room. The noise reduction performance for the ANC with the error suppression modules and without the error suppression modules are shown in the figures. So here we can see that with the error suppression modules, the wireless ANC has achieved around 5 dB higher noise reduction performance compared with the wireless ANC without the error suppression modules. And some experiments are taken in normal rooms to validate our proposed methods. Here we can see that in our experiment setup, the noise sources are placed in the corner of the two normal rooms, and a dummy head equipped with the ANC headphones are placed in the middle of the normal rooms, and the receivers of the wireless microphones are placed close to the ANC controllers. The ANC algorithms is implemented in the NI-PXI, and then a computer is used to control this PXI. The first experiment is taken to validate the noise reduction performance for the multiple noise sources. Two uncreated noise sources are employed in the experiment, and the sampling rate is set at 16 kHz, and all the filter lengths are set as the same for all the cultural filters. And for comparisons, a multi-channel wireless ANC and a wired microphones on the earcup for the ANC headphones and the commercial ANC headphones are used. So here we can see the noise reduction performance for each algorithms. We can see that our proposed methods and the wireless NCs has achieved almost the same noise reduction performance and have 4 to 5 higher noise reduction performance with only microphones on the earcups and the commercial NC headphones. This is because there is no unquality noise exist in the environment. So our proposed wireless NC, a hybrid combination wireless NC, is almost has the same noise reduction performance with the wireless NC. The octave band and the free power spectrum of the attenuated disturbance also shows that our proposed methods and the wireless NCs has a better noise reduction performance among all the ANC algorithms. And in the second experiment, we suppose that is unexpected interference occurred in the environment, which is not picked up by the wireless microphones. And this unexpected interference are composed of the central noise and a broadband noise separately. Other settings are the same as the previous experiment. Here we can see that our proposed methods have achieved the best noise reduction performance among all the ANC algorithms. Here that the wireless ANCs have achieved the worst noise reduction performance among these ANC algorithms because the unquality interference are not picked up by the wireless microphones. Power spectrum of the attenuated disturbance can clearly show that why the wireless NCs have the worst noise reduction performance among all the NC algorithms. We can see that the upper one shows when the interference is a central noise with 500 Hz, so that we can see that the wireless NCs has no attenuations for these central noises, and similar at the same time, if the interference are the broadband noise with 600 to 700 Hz. The wireless NC didn't pick up this interference, so it has the least noise reduction performance on this frequency band, and it has the worst noise reduction performance among all the NC algorithms. So at last, our proposed hybrid approach that uses wireless microphones and earcup microphones to acquire the reference signal with a high signal-to-interference ratios, and the error suppression modules is implemented to provide adaptive filters with individual error signals. Our proposed methods outperform with a wired microphones on earcup and a commercial ANC headphones with a noise reduction performance by 4 to 6 dB in a multiple noise source environment, and it is effective for undefined interference that occurred in the environment by 6 dB more than commercial ANC headphones. That's all. Thank you.